Assalamualaikum and have a good day. Welcome back to our class. All right. So today I'm going to give a lecture regarding process scheduling. Process scheduling, chapter 5. Okay. Okay, give me 1 second. I want to set the pointer. Maybe a pen. Okay. All right. Chapter 5, CPU scheduling. Okay. 5.1 regarding basic concept. 5.2 scheduling criteria. 5.3 scheduling algorithm. And then objective for this module, introduce CPU scheduling, which is the basis for multi-program operating system, and to describe various CPU scheduling algorithm. Okay, 5.1 basic concept. Okay, basic concept, Okay, give me 1 second. I need to, familiar with this desktop first. Okay, right. So maximum CPU utilization through multi-program, through multi-program. Okay, we need to, what we call this, achieve the target on CPU utilization, okay, which is optimum or maximum CPU utilization through a multi-program. And most processors exhibit the following behavior. Okay, first of all, CPU burst followed by I/O burst. CPU I/O, like this example. And then CPU I/O burst cycle, which is process execution, consists of cycle of CPU execution and I/O wait. I/O wait. And CPU burst distribution is of a main concern. Okay, so this is the figure, which is alternating sequence of CPU and I/O burst. You can see CPU burst, I/O burst, CPU burst. So it is alternate, It's like round robin. They give opportunity for the main program to have a CPU and also I/O. CPU, I/O. Okay, so this is default. Okay, this is, I can say, default concept or basic concept for the whole, in order to, implement a certain task, for example. Okay, this is the instruction. You can see that instruction, and then you have to wait, and then back to this again, continue, wait, and then continue, wait. So this is the scenario. All right. So CPU I/O burst cycle. Okay, if you can see this, like this example, similar that. I/O cycle, CPU burst, I/O cycle. Okay, this is what we call this. This is a part of the program, C language, C language. All right. Okay, this is histogram. Figure 0.2 representing the histogram of CPU burst time, right? Okay. Okay, this is the uh, CPU burst time. Yeah. So basically, they will started and then goes down like this. Yeah. Okay. And back to the maintain the what we call this the burst. Yeah, burst time for each of the process. All right. Okay. So job and process status. Basically, jobs. Yeah, move through the system. Yeah. Job scheduler, which is we have a long-term style or version, and CPU scheduler, which is for short-term. Okay, so we have a couple of, state they want to see. We got new state, ready state, running state, waiting state, and also finally terminated state. Okay, so all the process they need to go through this state compulsory. Okay, so means they will moving from one state to another state, and then this is controlled by the job scheduler. And also, if they want to move from ready to running state, there's nothing inside, just interrupt issue. And from running state goes to waiting, so there is a IO request page fault. Okay, there's some method or something to, let them moving from one state to another state. Yeah, like this running state to waiting state, there is a IO request page fault. And then from waiting state, there is another we call some interrupt, but here they call signal to continue processing. Okay, we can say that another method. We need something to initiate this waiting state goes to this state. Similar for others, like this, and accept ready to running, right? Okay, from this diagram. Okay, so the whole this they said is a controlled by the CPU scholar, sorry, CPU scholar, and then this one job scholar. This they're representing. Also, this one representing long term and also for the short term. Okay, long term, which is for the job scheduler, which is this. This is a long term. So, and then we have a very short, which is a spew scheduler. All right. So this is from new state to the final state, which is terminated. Okay, so they need to have these two, what we call this scheduler, yeah, long term and also short term. This is a diagram. All right. Okay. So based on that diagram also, yeah. So users submit a job. Normal, yeah. Normally, when user submit a job, first of all, job accepted and put on hold and place in the queue. All right. And then job state changes to new to ready, means indicates job waiting for CPU, and job state change from ready to running, which is when selected for CPU and processing. Yeah. And then job state, yeah, changes from running to waiting, require unavailable resources, and job state, yeah, changes to terminated, which is job completed, yeah, successfully and or unsuccess. All right, so this is the sequence of the task. And not really, so this is the kind of, they need to go through, you can say that, yeah, go through each of that. Yeah, all right. Okay, PCB and the queue. Okay, job PCB. Something like in the PCB is something that program control block, yeah, job PCB. So job in PCB created when job scheduler accept a job automatically, yeah. and then updated as a job executes, and then Q use PCB to track a job, very important, and contains all necessary job management processing data. PCB links to form Q, okay, which is job not linked. Yeah. Okay. So manage Q using scheduling policies and also some algorithms. Yeah. CPU scheduler. Whenever the CPU become idle, the operating system must select one of the processes in the ready queue to be executed. The selection process is carried out by the CPU scheduler. The ready queue may be ordered in various ways. CPU scheduling decision may take place when a process switches from running state to waiting state, right? And running state to ready state, and switches from waiting state to ready state. And also when a process terminates. Okay. So this is regarding CPU scheduling decision. Non-preemptive scheduling. For situation 1 and 4, where is 1 and 4? Reflect to this. Yeah, reflect to 1 and 4. Yeah, all right. So for situation 1 and 4, there is no choice in terms of scheduling. A new process, if one exists in the ready queue, must be selected for execution. Under non-preemptive scheduling, okay, non-preemptive, cannot interrupt. Yeah. Once the CPU has been allocated to a process, the process keeps the CPU until it releases the CPU either by terminating or by switching to the waiting state. Yeah. Okay. And then for preemptive scheduling, there is a choice, however. Yeah. For situation 2 and 3, preemptive scheduling can result in race condition. Race condition. Yeah. When data are shared among several processes. So it's create the condition called race condition when there is a data sharing. All right. Consider the case of two processes that share data. While one process is updating the data, it is preempted so that the second process can run. The second process then tries to read the data, which are in an inconsistent state. Consider preemption while in kernel mode. Yeah? Consider interrupts occurring during crucial OS activities. Virtually all modern operating systems like Windows, Mac OS, Linux, Unix use preemptive scheduling algorithm. Yeah, algorithm. Dispatcher module give control of the CPU to the process selected by the CPU scheduler. This involves switching context. Yeah, switching to user mode and jumping to the proper location in the user program to restart that program. Dispatch latency. Of course, there is latency. Every task, there is a latency. So latency means time it takes for the dispatcher to stop one process and start another running. So this is mean dispatch latency. Yeah. Okay. So this the one. Okay. Dispatch latency. Okay, present the same this scenario, the interrupt, and then this is the means by dispatch latency. So what they need to do? Save, and then restore, and this one continue executing P1. That's why they need to follow this kind of. Otherwise, they cannot. I mean, restart. Where to restart? First, they need to save first, and then restore, and then they start execute. Whatever they start, they will restart again. So in between this, okay, when they started interrupted, okay, from this PO, yeah, here, and then they begin again P1. So this they call dispatch latency. Yeah, all right. So dispatch latency, they give more diagram right now. Okay, so similar things, different, I mean, explanation. So response interval, and then there is inside the dispatch latency from event and response to event is a common one. So interrupt process. Okay, this is dispatch latency in the middle. Okay, so we have a conflict dispatch, and this is run always a time representing, and then process met. So this is different way they trying to explaining, yeah, about the dispatch latency. Okay, you can try to digest this, yeah, later. Similar. All right. Okay, concurrent execution of processes 1/3. Why they put 1/3? 1/1/3. Okay, we have dispatcher starting at address 100. We have process A 5,000, and then process B located at 8,000, and also 12,000 for the process C. Okay, and the program counter at B right now at the moment. Okay, snapshot of the example execution at extraction 13, cycle 30. I'm not sure this. Yeah, all right. Okay, so this is the scenario first. Okay, so in main memory, and then this is the program counter is pointed to this process B. Sorry, pointed to this actually. Yeah, they keep they keep the address for the program counter is very important. Okay, they will determine where to start. So actually, the contemporary counter is the address of the instruction in the memory. Where is it, and where it should start? Okay, every I mean, pointer is like the address of the starting. So program counter. So next program counter. Yeah. Okay, dispatcher. So it is say that starting at 100 dispatcher, and then if you can see 100, back to here 100. So I mean there is a 100 to 105, which is dispatcher. Okay, all right, like this. All right, and then this the process A started at 5,000 till 5,011, and also for the process B, and also for the process C. Okay, this is the detail of that. All right. So figure 3.2 traces of process of figure 0.1. Okay, this one. Yeah, all right. So next, CPU time or instruction cycle, which is 6 for each process. Yeah. So they make some assumption here. CPU time or instruction cycle equal to 6 for each process. Yeah. Assume all processes execute in sequence. And then with assumption no priority. Okay. So shaded area indicate we got a couple of shaded areas. This 4 altogether, right? Okay, 4 altogether. Okay. So these shaded areas indicate execution of this dispatcher, okay, dispatcher or dispatcher process, yeah. And then first and third column shows first and third column shows number of instruction cycle. First and third column. First, third column. And then second and fourth column shows address of being executed. Yeah, first and third. First column and third column. First column, this one, and third column, okay, shows number of instruction cycle. Second and fourth shows address of execution being executed. Okay, all right. Okay, A. Okay, and B. A and B. Number of instruction cycle. C. And A again. Okay, first A. I will start with A. And next B. And then back. Oh, it's a C. So A first. And then here we check this. Address for B, address for C. Yeah. And next, back to the A. Okay. Which started at 5006. This one 50 finish. And there goes 506 here. And next after that, C. All right. C left. Okay, because B done. So C, whatever they left, C. Okay, C here, 5. The last one, let's stop. Because this one reflect to CPO, sorry, CPU, IO, CPO, and then IO burst. After that, and then now back to here again. Okay, this is the what we call the algorithm and how it's work. Yeah. Okay. Okay, they represent through this same thing. Yeah. Okay, try to understand this. All right. Next. Okay, the following table shows, okay, the same again. We give another analogy to, increase your understanding about this. Yeah, A, B, C. And then they give the same scenario also, dispatch, then the address for each of them. Okay, please. Okay, read this and digest it and try to understand. All right. Okay. So, okay, I just give explaining about this. Or they straight away. Okay, the same thing that I explained just now. So they will reflect to this. Okay, go through this. Okay, video also and also the slide. So it will help you to understand. Yeah. Okay, what is this? Dispatcher. Okay, there is a dispatcher. This is a go straight answer. So everyone there in a dispatcher is very important. Okay. Every time the dispatcher here, here, and so on until finish. Okay. And then final one, this is very important. Okay, so maybe this I'm not sure whether it can be a question for you, like what is the process state for each process at A, Y, and Z, okay, or Z. Justify your answer. So at this time, okay, so what happened? So process A, in what conditions? They're running. Process B is a ready queue. C, what? And also dispatch. So then you need to explain based on these processes at this time, X, and similar to this Y, and also Z. Yeah. Okay. This kind of the question maybe they will ask. Okay. All right. Okay. Scheduling criteria. Okay, CPU utilization. Keep the CPU as busy as possible. So this is, I can say, it's like common. Yeah, keep busy. Okay. Don't let your busy is idle. Similar to our daily life also. Okay. Here they keep busy. Yeah. So this is, can say, CPU utilization. So for the optimum, until optimum level. Okay. Throughput, the number of process that complete their execution per time unit. Okay, example, 5 per second. And then turnaround time means amount of time to execute a particular process. Waiting means total amount of time or process has been waiting in the ready queue. And then response time, amount of time it takes from when a request was submitted until the first response is produced. Okay, not output. Okay, especially for the time sharing environment. Okay, so this is a term normally to check, okay, in scheduling, in order to create the schedule. This is all the parameter. Okay, similar that at the beginning I'm talking about the latency. Okay? Same thing for this. Yeah, so this is all the parameters, okay, for scheduling criteria. So exercise, you can do it. Okay, again, they will, okay, lots of exercises is very good. So you can try this. Yeah, okay, based on my lecture and also the notes. So optimization criteria for scheduling. Maximum CPU utilization. So the best is 100%. Keep busy 100% of the time. So all the time busy. It's like a flight traveling. There's non-stop. Okay. Every 24 hours is just like when they arrive, they will departure, just stop for a while and then depart again like that. So similar to this, goes for the maximum CPU. This is the main criteria, or is the main achieve, or main target, or main, what we call this, the result. They need to achieve that. It keeps CPU busy 100% of time. And then maximum throughput, of course, run as many jobs as possible. This is also the targeted. Okay, for each of the algorithm you created, in order talking about optimization, so these are the things you need to achieve that. So if you can achieve that, so your scheduling is good, something like that. Okay, because this is based on my experience, not because we have to go through the paper journal to check, yeah, the criteria of the scheduling. Sometimes the scheduling is for this and that, this and that, this and that. Okay, this is the normal criteria, normal parameter that when we develop, we need to achieve. So here in this class, we have to explain. So this is the term that we use, what for, yeah. So minimum turnaround time. So move entire job in and out of system quickly, and for minimum waiting. So also can be one of the, targeted for each of the algorithm. Okay, what for? So move job out of ready queue quickly, and minimum response time. So means quickly turn around interactive requests. All right, scheduling algorithm. Based on specific policy, allocate CPU and move job through system. Yeah. So algorithm types: FCFS, first come first serve; SJF, shortest job first; RR, round robin; priority, and multi-level queuing scheduling, and many more. Yeah. And also current system emphasize interactive I can say that current system emphasize interactive use and response time. So use preemptive policy. All right. So maybe it could be one of the targeted for the current. I don't know. So basically we have to check, okay, on the current paper journal. Right. So first come first serve scheduling, which is it is stated that first come first serve is a non-preemptive job handled based on arrival time. Earlier job arrive, earlier serve. Yeah. Considering the following three processes and their burst time. Okay. So we have P1, P2, P3, and this is each of the burst time for each of the processes. And then suppose that the processor arrive in this order, P1, P2, and P3. Okay, we use Gantt chart to illustrate a particular schedule. Okay, this is the schedule. So it's like 24 verse 10, 27, and 30. And then this is the waiting time. Okay, for the P1, P2. Okay, and this P3 waiting time. Okay, and then average waiting. Okay, then divide by 3. All right, so average waiting. So this one waiting time for each of the processes. Yeah, P1, P2, and also P3. So suppose that, okay, still under first come first serve. Suppose that processor arrive in this order. Yeah, P2, P3, and P1. So this is the scenario, and this is the waiting for each of the processes, average. And if you look, they conclude that much better than previous case. Okay, and then it is convoy effect, short process behind a long process, of course, and consider one CPU bound and many IO bound processes. And then for the first come first serve example 1, okay, so 3 processes arrive in order. We got job A, job B. Okay, this is the first time as well. All right, so this is the wait arrive in order at T0 with different CPU bursts. Okay, so in sequence A and B. Okay, like this example. Oh, sorry, this example. Yeah, in order. Yeah, all right. Similar that our explanation just now, same. Yeah, so just click this and then you can check all this whether it's correct or not. Yeah, all right. And then for example 2, they got different sequence. Okay. Okay, right. So please check that also. All right. And then what is this? Extra, another. So 3 process arrive at different time with CPU burst. Okay. And then this is also exercise 1, some extra. Say that and got solution. Can go through that, double check. All right. So as a conclusion, good for the batch system, unacceptable, ineffective. Okay. Finally, the decision. Yeah. So this is a decision. So this first come first serve. So that's why this algorithm depend on the application wise. Sometimes they good for certain part, maybe good for another part. Yeah. So not all is suitable for all condition. So the advantages, average waiting and turnaround time varies, and also seldom minimized. Convoy effect, whereby short processes queue behind a long process. So result in lower CPU and device utilization. Yeah. All right. Next, SGF or SGN, shortest job next. Okay. All right. So this is a non-preemptive. Okay. SGF, shortest job, also known as the SJN, shortest job next. Associate with each process the length of its next CPU burst cycle time. Use this length to schedule the process with the shortest time. SJF is optimal. Yeah, give minimum average waiting time for given set of processes. How do we know what is the length of next CPU request? Could ask the user. What if the user lies? Okay, that's the things. Okay. Okay, consider the following 4 processes and their burst time. Okay, and this is the CPU scheduling chart. Okay, right. So we did this kind of scenario, but different content and different algorithm. Yeah. So please go through this also. Please check. And similar to example 3 as well. Yeah. Okay. So, and the rest of this also very straightforward. Yeah. So go through. Okay, finally, SJN and SJF, easy implementation in the batch environment also, and CPU time requirement known in advance. Yeah, does not well in interactive system, and then it is optimal algorithm. All jobs are available at the same time. CPU estimation are available, and more accurate. Okay, comparing so far between first come first serve, or maybe among, because it doesn't mention. Okay, more accurate between what? Okay, so in general, yeah, if 2 processors have the same CPU burst, yeah, FCFS may be used. Okay, so maybe I can say that just comparing with the first come first serve. Okay, all right. So this also the another exercises. This is exercise 2. You can try this and then understand that. Yeah. So through this, we call this slide, and also through this video as well. Yeah, you can go through and check. Yep. Okay. So shortest remaining time first. Another one. Okay. We have shortest remaining time first. This is a preemptive version. Okay. And then different name, shortest remaining time first. So processor allocated to job closer to completion. Preemptive if the new job has shorter completion time. Okay, they are looking for this kind of the processors which has shorter completion time. This. They were looking, okay, throughout the system. Yeah, correct. So example illustrating the concept of varying arrival time and preemption. So process, we got process P1, P2, similar that, okay, we did for the previous one, similar kind of the, the gift, but different scenario, okay, because this is different algorithm. Yeah, okay. 1 second. All right. Okay, so different scenario, of course, it's different. Okay. All right. So same thing, yeah. Average time, okay, the process, and also the average waiting time, right? So example 4, okay, we got burst time and also arrival time. Okay, so they give a jobs in sequence. This is a Gantt chart, job A, B, C, and then again we got the remaining. That's why they return this. Also job D and job A again. Yeah. All right. So timeline job A, B, C using the preemptive SRT algorithm. Each job is interrupted after one cycle if another job is waiting less than CPU time remaining. Okay, this is very important. Every cycle, so each job is interrupted after one CPU cycle. Okay, one CPU cycle. They will interrupt after one CPU cycle, means they will check which job is waiting with the less CPU time remaining. So they will give this priority. Okay, please take note. Okay, this is the mean by SRT. Yeah, all right. Okay, just play this. So every time they will check at this stage. Yeah, the point is here, at here, the regular will check which job. Okay, got a remaining. Okay, and then they will do that job first. Okay, all right. The same thing they will create. So this is completion time for each of the finally for each of the process. Okay, and then this is the same thing that you need to calculate the turnaround waiting time also. Yeah. And another example 5, different scenario. See, different job spec and then CPU burst, what time CPU burst, all right. Then what's different? Timeline for the same job sequence A, B, C, D using non-preemptive SGN algorithm. Okay, job A initially in the ready queue, so it run first and continue with the rest. Okay, we start. This is timeline. Yeah, timeline. So similar that from the previous, but different. This one for shortest job next. Yeah, all right. Okay. So this is how they when they running that. So this in queue, they will keep on changing after they check the remaining of this. Okay, so which they will process every cycle. They will check which job they should do based on the remaining time, right? So they will choose. Okay, so you have to go through this. Yeah, this slide, this video, and so the slides. Yeah, right. Okay, this is the calculation, the same thing that you need to go through each of them. So finally, SRT often used in the batch algorithm. Okay, so shortest job given a priority. So this is kind of the priority. There is a priority. So that priority not just give the shortest remaining. Where's the remaining is the lowest than the CPU cycle, they will give first. I think, yeah, that's the thing, right? Okay, so please check that. And then cannot implement in interactive system, yeah? And then require advanced CPU time, low knowledge, okay? And then involve more overhead than SGN and also SJF. System monitors, yeah, CPU time for ready queue job, yeah, perform context switching. So involve more overhead compared to this SJN because there is a context switching, always changing, always changing, always changing. Okay, this is context switching. And also monitoring CPU time. So this one become overhead. They need to keep on monitoring CPU time for ready queue job. Okay, this is overhead. Okay, extra job. Okay, they need to do instead of compared to this SJN. Okay, normal SJN, nothing. Just follow the sequence. Because this SRT, okay, SRT need to do extra job to monitoring. Okay, but at least finally you can have this shortest job given priority. So this is important, right? Okay, so there's a depends on the target achievement, what you're going to achieve. Yeah, right. Next, round robin, RR. So preemptive, used extensively in interactive system. Yeah, the system. Each process gets small unit of CPU. So each unit, so this small unit they call here, they use the word time quantum or Q. All right. So after this time has elapsed, the process is preempted and added to the end of the ready queue. What's the queue algorithm? First come first serve. Time quantum size crucial to system performance. Okay, doesn't know, depends on their target. Okay, not sure how long, but there is a time they will allocate to each of the process. Yeah. So you say here varies from 100 millisecond to 1 or 2 seconds. Because right now modern computing they got very fast, you know. So that's why the time if too big, they will not achieve. It's like cache memory. If you put the large, it doesn't give anything. I mean the meaning of the cache memory. Okay, if it's too big, because that's why the cache memory there is a simple, there is optimum size depend on the how big your storage. Okay, the instruction. There is an optimal size, and we cannot simply put like what we call this your hard disk drive. Okay, as big is good. No, similar for this. Yeah, time quantum. There is a specific time based on this system performance. Please take note. Yeah, like a cache memory. Okay, all right. If there are n processes in a ready queue, the time quantum is q, then each process get 1 over n of the CPU time in chunk of at most q time unit at once. No process waits more than n minus 1 q times unit. This is the very important, okay, for this round robin. Please take note. Okay, so timer interrupts every quantum to schedule next process. Okay, they will keep on timer. There's a timer. Okay, of course, they need to use a timer to execute each of the instructions. This is a common. Yeah, all right. And also I can say this is a algorithm for the round robin. Yeah. So if CPU burst bigger than time quantum, so what happened? Job preempted and placed at end of ready queue. And also, what they do next? Information saved in PCB, program control block. Keep it there because later we'll come back to this process. We'll get the information to return. So everything is saved there. Just read where we should start. Okay, that's the things. Okay, please understand. At the beginning, we already mentioned about this because once you need to goes to another process, you need to save first in PCB. And then after that, you return, read back where it is located in the memory, this PCB. Okay, we need to get the information where you should start. Otherwise, it will go this and that, haywire everything. Okay, so that's why. These are very important. All right. Okay, next. So if job CPU burst, yeah, less than time quantum, less than time quantum. So either job finish or interrupted by IO request. and then allocated resource for job finish, allocated resources released, and job returned to user. And for the information saved, next for the interrupt. So that's why I say that just now, save in PCB and link to the IOQ. Later we come back. One request satisfied, job return. That's the things. To end of the ready queue and wait for the CPU. So that's very important. Okay, when the interrupt finish, fine. We don't need to return. Yeah. Yeah. But when there is unfinished job, which is interrupted, unfinished job. So things first, you have to save in PCB. That is very, very important. All right. Okay. So efficiency depend on the time quantum size in relation to average. Yeah, in relation to average CPU, burst quantum too large, larger than most CPU. So algorithm reduce to first come, first serve. Okay, and then is a quantum too small, context which is occur. What happens? Job execution will become very slow. Overhead dramatically increase. This is what happens if they choose this too small. Okay, all right, based on their result. Okay, I give this the explanation. What the end? What happened? Okay, to your algorithm if the quantum size is too small. Okay, all right. So example of RR or round robin with the time quantum 4. Okay, so consider the following 3 processes. Okay, same again, same scenario. Okay, and also same kind of the explaining the scenario. Oh, we got the burst time for each of the processes. Okay, 24, 3 for each for P1, P2, P3, and 24 burst time for P1. Yeah. Then this is a Gantt chart. P1, P2, P3, P1, 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 P1. Yeah. Okay. And then the average waiting time under RR policy is often longer. Typically higher average turnaround than SJF, but better response. Okay, Q should be large compared to context switch time. Then Q is usually 10 millisecond to 100 millisecond, and context switch less than 10 microsecond. Yeah, micro. Okay, all right. Then this example 6. Okay, so you can go through this. Okay, by your own. All right. Check whether this slide is correct or not. Yeah. Right. I just play and double check that one. Okay, how it will check every. Can see that every time they will check. Okay, it's like similar that shortest job next, shortest job remaining, SRT, shorter remaining time. So similar for this also, they will check every time because they need to do pass, okay, to the next process. So every time they will check, okay, and then pass to the next process. All right, double check this, yeah. Okay, so this is time around calculation for each of the job, and then average turnaround time for the whole job. Okay, this is some extra. They give a lot of example here. Okay, just go through this video and also the slide. Okay, play on that. Okay, what is this? Time quantum and context switch time. Yeah, the performance of RR algorithm depends on the size of the time. Finally, they say this. See, this is like the we already use this for the certain job, and then they come because normally all the algorithm came from the research work, and we come to the to this books, make it the books, and then to this class, so to explaining the concept. All right, operating system. So the performance of RR algorithm depends on the size of the time quantum. Okay, this is the they found that. Okay, so basically depend on time quantum. So there is a optimum size of the time quantum. Okay, in order to call to get a better performance. I'm not sure how to get a better, what parameter, how, but through the sentence. Okay, by the sentence, the size of the quantum will determine the performance of the RR. Okay, so if the time quantum is extremely small, it is say that here, say 1 milli, for example, RR can result in a large number of the contact switch. Okay, too small, so many times repeating. Like the example, okay, below here. Okay, so I need to check. Okay, all right. Okay, time quantum is 12, so contact is 0. Let's say here, time quantum is 6, so only 1. So here, time quantum is 1, so contact switch, how many? So they need keep on monitoring every, so 6, 9 times. Check based on this figure, yeah? All right. Okay, all right. So turnaround time varies with the time quantum. Okay, the average turnaround time of a set of processor does not necessarily improve as the time quantum size increases. All right. In general, the average turnaround time can be improved if most processors finish their next CPU burst in a single time. Okay, this is the finally decision that, okay, but not we call in the real situation cannot, it will not happen, right? So anyway, we doesn't know. Okay, we doesn't know. Okay, we doesn't know whether the CPU, because the processor, because if I server running lots of data, running on, because let's say it's Netflix, for example, receiving lots of demanding, because many user, 1,000 million user every single, every single second we receive so many connection. So at the small, yes, but there is a calculation, because in general there is a calculation to calculate that. Okay, try to imagine in the big scale. Okay, this is small scale. Okay, how for the explanation we use a small scale, yeah? All right, to explaining the scenario. All right, so this is the thing that from this graph, okay, try to understand this. So, and this graph, yeah, process time and also time quantum for each of them, yeah? Okay. So these are an example 7, we got quantum 10, and then we got job A, job B, and so on. Job A, quantum 5, and then what happened to the rest. Okay, please check, yeah? This similar kind of the things. Scenario, same, but different algorithm, yeah? Okay. Okay, finally, all right. So overhead become costly and turnaround time suffers because of that scenario. Okay, what's the scenario? Based on the case. That's why there is a case A, case B, and case C different. Okay, so you can see the job A. So how long? This is how long, and time quantum also. It will reflect the result. All right, please check that. Okay, another one, priority scheduling. Priority numbers actually in integer. Yeah, priority is a common. Okay, if you want to put it, to execute first, give a high priority. Is a common. Every in network, everything is a priority. Put a priority. VVIP is priority. So many priority. Okay, so now in scheduling also there is a priority scheduling. Yeah, scheduling. So priority number, basically they use a number integer, is associated with the each processes. Yeah. So this CPU is allocated to the process with the highest priority. Smallest integer equal to highest priority. Okay, so this is we're using this kind of depends. Okay, different algorithm, different, but this algorithm smallest represent highest priority. Okay, so means that preemptive and non-preemptive. So means possible to do what? Preemptive and non-preemptive. Yeah, if we got this priority. So this priority will do preemptive and non-preemptive to the current process. Yeah. SJF shortest job first is simply of priority scheduling where it is used the inverse of the next CPU burst time as its priority. They are put their main, right? Right. The main, what we call this, main target, main goals for each algorithm. And we already explained this before. Yeah. So the smaller the CPU burst, but the higher the priority. Okay. If two jobs having the same priority and they are in a ready mode or in the queue, for example, it works on a first come, first serve. So there is their own algorithm. Can be anything. Okay. So here, priority scheduling is mentioned that. Okay. So this is something I can say is like a condition or maybe special condition. Okay. All right. So problem starvation mean low priority processes may never execute. Okay, they found that when they try to implement this, okay, there is a starvation condition where low priority process may never execute because it's very low. Because we already give a high, so the low we miss. So this is starvation algorithm. Sorry, starvation mode of starvation. This is a problem. So the solution, they come with the aging. They say that as time progresses, increase the priority of the process. So they will put the increasing the priority until this will be because the low priority process. Okay, all right, understood. All right, the low priority because here they use the high number, smallest integer, which is high priority, right? This one. Okay. So this is the way they solve by using aging technique where they increase the priority. Okay, means that the smallest they put the number become getting lower, smaller, right? Okay, because smaller is higher. All right. Okay, this is priority scheduling. So example of priority scheduling, okay, you can go through similar that for the previous one, just go through that and then compare and then check whether it's correct or not. If there is something wrong, please let me know. Yeah. Okay. Then system admin. Oh, one slide only. Okay, good. Next, system administrator or process manager use different method of assigning priorities. So depend on your algorithm. Okay, for me. Process manager priority assignment method. We got memory requirement. We have number and type of peripheral devices. Total CPU, amount of time already in the system. Okay. So the aging. Okay, memory requirement means job required large amount of memory and then allocate lower priority or vice versa. And for the number and type peripheral devices, job requiring many peripheral devices, allocated lower priority, vice versa. And then for the total CPU, which is job having a long CPU burst and also given a lower priorities, vice versa. And then amount of time already spent in the system. So total time elapsed since job accepted for processing, and increased priority if job in system unusual, which is unusual long time. All right. So this is exercise 3. So they give you 5 jobs, similar way. Just analyze this, whether true or not, and let me know if there is something weird about this slide. So so I will correct in future. Yeah. All right. Thank you. Exercise 3 and combining. So there is some reason they improve, because this is the kind of the research. They will combine lots of things because depend on their job in order to achieve what. So there is some target because we don't know, because this is general explanation. Yeah. Okay. So now combining priority scheduling with round robin. Okay, this is possible also. Doesn't matter because there's some reason why they combine. There's some reason we need to read their paper. We need to understand. We need to know that, because they combine because of what? We doesn't. Okay. So let we continue this first. Yeah. Okay. System execute the highest priority process. Processes with the same priority will be run using RR, round robin quantum equal to. Consider the following 5 processes and their burst time. Similar way, let's try to explaining. We got priority. So identify the priority first. Okay, and then if 2 processes has the same priority, this is already mentioned. So this kind of thing that when there is a similar, they goes or they set. Or here they said they will apply first come first serve, and then this is the Gantt chart, similar scenario. They will try to explain, and then this the average weightings. You can double check that also. Okay, they try to combining, try to understand this one. Yeah, all right. And then this is the result. Please check. There is something wrong on this slide. Please, yeah, let me know. Okay, next we got multi-level queue, hybrid environment. Okay, ready queue is partitioned into separate queue. We have foreground and also background. Foreground for interactive and background for the batches. All right. So process permanently in a given queue. Each queue has its own scheduling algorithm. Okay, for the foreground, they use RR. For the background, they use first come, first serve. Scheduling must be done between the queues. Yeah. Fixed priority scheduling. In example, serve all foreground, then from background. Possibility of starvation, of course. And then time slice. Each queue get a certain amount of CPU time, which it can schedule among its processors. An example, 80% to foreground in RR, 20% to background in first come, first serve. Separate queue for each priority. Is it same or not? Maybe same. Okay, now a separate queue for each priority works in conjunction with several other schemes. Okay, so that's why I told you that there is a many kind of the start. So here they try to explaining about the separate queue for each priority with in conjunction with several other schemes. Works well in system with job group by common characteristics. So we have priority 0, 1, 2, and 3. So which one they will use first according to our notes? They will start this first, correct? Okay, please correct me if it is wrong. Because the lowest integer become higher priority. Okay, just mention this note, right? Okay, please. Yeah, check that. So 4 primary methods. First, not allowing movement between queue. Second, movement job between queue. And then there is a method for variable time quantum for per queue. And then aging, giving special treatment to job that have been in the system for a long time. Okay, as we learned in the previous content, which is the keep the value of the become the highest or reduce the number of the integer, which is it become the highest priority, right? So you can know. So this is the things. So 4 methods. Okay, 4 methods. Case 1, no movement between queues, simple. Reward high priority jobs. Processor allocate using first come first serve. Processor allocate to lower priority jobs only when high priority queues empty. And then good environment, which is few high priority jobs and spend more time with the low priority job. Okay, no movement between queues. For example, okay, we have tried to check this arrival job first. Job 1, job 2, job 3, and job 4, job 5, and then which one they will go first based on that. Please double check that, yeah. And then after that, which one they should start first? High priority, next low priority, and so on. Okay, please go through this video and also the slide. Okay, make you understand more on this case 1. Yeah. Case 2, processor adjust priority assigned to each job. So higher priority job, initial priority favorable, treated like all other job afterward. And then quantum interrupt, so job preempted, move to the next lower queue, may have priority increase. And good environment, job handled by cycle characteristic, CPU or IO, and then interactive system. All right. Then this example, please check for me. Yeah. If something wrong, please let me know. Okay. Next. All right. And then they set the priority, and then which one? The high priority first, and then the remaining put back in the low priority, then process the next, and so on. Okay. The rest. Okay, until J1 finish, until J2, yeah, complete. All right, so case 3, variable time quantum per queue. So it's a variation of movement between queues. Okay, each queue given time quantum size. So size twice as long as previous queue. Fast turnaround for CPU bound jobs. CPU job execute longer and a given longer time. So finally improve chance of finishing faster. I/O bulk jobs such as printing, sales of document have many brief CPU bursts and long I/O cycle. CPU jobs, CPU bound jobs such as finding the first 300 prime numbers have a long CPU burst and short I/O cycle. So it depends on the task actually. Yeah. All right. So you can check these kind of things similar. Okay, and then next, what they should do. Okay, J3, then same thing. Okay, all right. J2, then done. All right. So case 4, aging, ensure low level queue job eventually complete execution. And then system keep track of the job waiting, keep track on that. And then if too old, system move job to the next highest, continue until all job reaches top queue, and may drastically move all job to the highest queue. So advantage cuts again indefinite unwilled job postpone. Yeah. So J1, J2 arrive, and then they check the priority. So J2 in the in the higher priority, J1 in the lower priority, and then J2, J1, okay, which one? Higher priority first, J2. Okay, they will process that. And then at that time, J3, J4 arrive, then put, but J2 still running, yeah. And then they say here T50, okay. J1, CPU bus 9, J2, J3, J4 here. Yeah, I want to check here. Very important. CPU bus for each the process. So 1, 2, 3, and then 2 is quite long. We got 100 is the highest. 100 CPU burst. Okay. And then what happened at T0, T70, for example, next job arrived, J5 is a higher priority, J5, which is J5, higher priority, this one. It becomes the high priority, they arrive at T70, for example. And the same time, J2 now is running because they got CPU was 100. And then J1 has been waiting 70 CPU time in order to complete, right? Okay, and then change move to the high priority. Okay, all right, J1 also waiting so longer, move to the high priority, and then J1 process, J5 process at T0. After complete J2, they start give another one based on the priority. All right, okay. So multi-level scheduling. So based on high priority, which is system process, interactive processes, interactive editing process, batch student processes. So this is the level of the process they give it to each of the process. Yeah. Okay, this is comparison among all the all those algorithm that we mentioned in our chapter today. Yeah. All right, multi-level feedback. A process can move between the various queue. Edging can be implemented this way. The idea is to separate process according to the characteristic of their CPU bus. Multi-level feedback queue scheduler defined by the following parameters, which is the number of queue, schedule algorithm for each queue, method used to determine when to upgrade a process, and then method used to determine when to demote a process, and method used to determine which queue a process will enter when the process needs service. Yeah. So for example, multi-level feedback queue, we have Q0, which is RR with quantum time quantum 8, and next Q1 RR time quantum 16, and Q2 first come first serve. Yeah, all right. So we have multi-level feedback queue. Okay, this is the multi-level feedback queue. Multi-level. Okay, quantum 8, quantum, and then finally first come first serve. Okay, scheduling a new job, enter queue, which is serve at first come first serve. Okay, this algorithm when it's gain CPU, job receive 8 millisecond. And then if does not finish, similar that, okay, we just follow this kind of algorithm. So this is algorithm for this multi-level feedback queue. Just go through this. And here, what else? And then process in Q2 are run on a first come first serve basis, but are run only when Q0 and Q2 are empty. All right. And then this scheduling algorithm give highest priority to any process with the CPU burst of millisecond or less than that. Yeah. All right. So this kind of multi-level feedback queue. Okay. Then this is an example. Sorry, the example. That's a size 9. Okay, please go through this. Yeah. And also this video. Okay, just play around quantum 1. Okay, first, and then JE, next JA. Yeah. After that, based in sequence, look for the what we call here, yeah, this is the Gantt chart, yeah. So go through each of that, and JD, after that complete, go to the another queue. So first come, first serve, which is the next one. Then finally, this is how they get the all this value for waiting time, turnaround. Please check. Yeah. All right. Okay. That's a completed. Because just now, feedback time. Yeah. Okay. Multi-level feedback queue. Okay. This is the another example of the questions. Just go through this similar. All right. Okay. Summary. Finally, process manager allocate CPU among all users. Okay, job scheduler assign job to ready queue based on characteristic. Process scheduler instant by instant allocation of CPU, and schedule algorithm is unique, characteristic, objective, and application. And system designer selects a best policy and algorithm after careful strengthen and also weaknesses evaluation. All right. Okay, end of chapter 5. Okay, that's all for chapter 5. We'll be continue on next chapter later. All right, till then, thank you for watching. See you in the next module. Assalamualaikum. Bye-bye.